Hi everybody. We are now going to pursue our discussion on functions by discussing continuity. We're going to examine both continuity at a point and over intervals. When you think of continuity, there's a pretty good chance that you will think that it represents a function that we can draw without lifting our pencil. This intuitive explanation is actually quite accurate, as long as you have a pretty clear idea of what the graph of the function is. In this section, we'll define continuity at a point or on an interval using terminology that is a bit more formal. First, let's start off by thinking of what would prevent a function f from being continuous at x equals a. A few scenarios could arise. We could have an infinite discontinuity, which is also called a vertical asymptote. In this image, you can see that as x approaches a, whether from the right or the left, the function's y values tend to become infinite. In this function, a step occurs at x equals a. The limit as we approach a from the left does not agree with the value for the limit as x approaches a from the right for f, which causes this jump between values. A discontinuity could also be caused simply by a hole, which is what occurs when the function's value at a disagrees with the function's limit as x approaches a. So here is our definition for continuity at a point. Suppose f represents a function. F is continuous at x equals a if and only if its limit as x approaches a for f of x is equal to f at a. Now there's a way to proceed using a three-step check whether or not the definition is satisfied. You can first and foremost determine if f exists at a at all. Then, determine if the limit of f of x as x approaches a exists. This may require that you investigate the two one-sided limits, because recall, the limit as x approaches a for f of x is well defined as long as x approaching a from the left of f of x and x approaching a to the right of f of x agree. Now, if f of a and the limit both exist, these values should also be equal to one another. Here's an example where we'll examine whether or not f at x equals 2x minus 4 over x squared minus 4 is continuous at x equals 2. We're going to use the three-step check to determine for continuity at x equals 2. Firstly, does f of 2 exist? Well, actually, no. F at 2 is undefined due to a division by 0. We could already stop at this point and conclude that f is discontinuous at x equals 2. We'll keep going in our three-step check for a reason that I'll explain in a minute. Does the limit as x approaches 2 for f of x exist? Well, in this case, when we try direct substitution, a 0 over 0 form is obtained. And as you can see, I've performed the limit by finding common factors to the numerator and denominator, and through simplification, the limit itself actually reveals a value of 1/2. So the limit for f of x as x approaches 2 does exist and is equal to 1/2. Does f of 2 and the limit for f of x as x approaches 2 agree? Well, no, because f at 2, as we saw earlier, simply doesn't exist. Here's what is happening graphically. The limit does exist, as you can see. Approaching x equals 2 from the left or from the right makes the function tend towards a height of 1/2. However, the dot is not filled at 2 itself because f of 2 is undefined. This would be a discontinuity due to a hole. Considering the exact same function, f of x equals 2x minus 4 over x squared minus 4, we're going to determine whether it is continuous at x equals minus 2 this time. Again, same three-step process. Does f of minus 2 exist? Once again, the answer to that question is no, because of a division by 0 when x is replaced by minus 2. Does the limit as x approaches minus 2 for f of x exist? This time, direct substitution actually reveals a minus 8 over 0 form. If you recall from previous videos, this is an indication of an infinite behavior. So I've investigated both one-sided limits in this case on the left. As x approaches minus 2 from the left, a minus 8 over 0 plus form is obtained, which means a negative infinite behavior. On the right, as x approaches minus 2 plus, the function reveals by direct substitution a minus 8 over 0 minus form. So the signs cancel off and we get a positive infinite result. These are indications of the existence of a vertical asymptote at minus 2. Graphically speaking, we'll see that neither f of 2 and the limit exist. This is because no dot is observed for an x component of minus 2. And furthermore, we have the infinite behaviors for both the left and the right-hand approaches. Again, this is a discontinuity at minus 2 caused by a vertical asymptote, or what we could call an infinite discontinuity. Here's a third example, which consists of a piecewise function. The function we're considering right now is defined as being equal to sine of x minus 1 over x minus 1 for all x's left of 1. The value of f of x is 1 specifically when x is 1, and the value of the function is x squared minus 1 over 2x minus 2 for any x that is greater than 1. So we have three rules depending on the value of x we are using. Three-step check once again. Does f at 1 exist? Well, if we recall what the function was defined as, it was explicitly written that the function's value for an x value of 1 was 1 itself. So by definition of the function, f at 1 exists and is equal to 1. Second part of our check, does the limit as x approaches 1 for f of x exist? Since this is a piecewise function whose rule changes to the left and right of 1, we will have to examine the one-sided limits. As x approaches 1 from the left, sine of x minus 1 over x minus 1 creates a 0 over 0 form. But remember that sine of x over x as x goes towards 0 is a special limit form. And this limit form is also observable here, where x minus 1 plays the role of the angle. The divider is x minus 1, and both the angle and the divider are tending towards 0 as x approaches 1. So by the result of the special form, this limit value is 1. As x approaches 1 from the right, a 0 over 0 form is once again obtained by direct substitution. However, an x minus 1 factor is observable in both the numerator and denominator and can be cancelled, and by doing direct substitution in the simplified form, a limit of 1 is obtained. So, in conclusion, we have a left and a right-hand limit as x approaches 1 that agree to equal 1, and therefore the limit as x approaches 1 of f of x is 1. Third step of our check. R values for f of 1 and for the limit in agreement, and the answer is yes, as both have produced an answer of 1. Here is what our graph would look like, with the filled dot at 1 being the definition that was given in our piecewise function for the specific value x equals 1. Left of 1 is the graph of the function sine of x minus 1 over x minus 1. And to the right of 1 is a graph of the function x squared minus 1 over 2x minus 2. Notice how left hand, right hand, and the function's value at 1 all agree to meet. Let's have a quick discussion on continuity on intervals. Now basically, wherever you can draw the function without lifting your pencil would form the intervals of continuity. I've provided a graph that is a piecewise function with different rules on different intervals. It appears as though the function is continuous until we encounter a first hole at x equals minus 6. Therefore, the function is continuous to the left of minus 6. Past this hole, the function remains continuous until we get to that second hole where a jump takes place at minus 4. So the function is continuous between minus 6 and minus 4 exclusively. At x equals minus 4, a filled dot tells us the function exists at that point, and a continuous interval is observed until we get to plus 4, despite the bump that occurs at the origin. So continuity is guaranteed from minus 4 to 4 inclusively. And then the last piece of the puzzle is the continuous nature of the function beyond x equals 4 and to infinity. So x greater than 4. So there are 4 intervals where the function is continuous. More generally, the following functions are continuous on their domain. So if you can identify their domains, you will also identify their intervals of continuity. Polynomials are continuous on their domain, which consists of all real numbers. Rational functions are continuous on their domain, which means anywhere the denominator is not 0. Root functions are continuous on their domain. This may depend on whether the root is odd or even. Sine, cosine, tangent functions are continuous on their domain. So in the case of sine and cosine, that would be for all reals. For tangent, we have asymptotes that occur periodically. Exponential functions are continuous on all real numbers. Logarithmic functions are continuous as long as their argument stays positive. Absolute value functions are continuous on their domain, which is all real numbers. And then combinations of the above may require that we investigate the domain more extensively. A few quick examples. P of x, 2x cubed minus 5x plus 7, is continuous on all real numbers. In other words, we can draw this function without ever lifting our pencil, and this is because it is a third-degree polynomial. The root of x minus 2 is continuous on the closed interval 2 to infinity because this function's domain begins with x equal to 2 and prolongs to the right. G of x, in this case, is a rational function, 1 over x squared minus 1, and its domain excludes any numbers that create 0 divisions. So we have to exclude 1 and minus 1. Therefore, g of x is continuous on its domain, and that would mean over the intervals minus infinity to minus 1, minus 1 to 1, 1 to infinity. Notice how we've excluded the points of discontinuity to create the 3 separate intervals.